Go ahead.
Okay. Before I go on, could you please raise your hands if you have experience with Google Colab, or with working on Google Colab? Because I plan to very quickly go through its functionalities. Please raise your hands if you have experience. Okay, so I get that you don't have so much experience. So let's start with some introduction. And as Stelio says in the chat, we have a Slack channel. So if you want to ask some questions, please do it there and not on the Zoom chat. Okay.
Christo, I can't find the raise hand button.
Let me see. I think it's you go to, where is it? I'm not sure, to be honest. Wait. Okay, I cannot find it here, so please just write down. No, it's if you go to reactions, next to share screen, you can find a raise hand button.
For me, it's participants, chat, share screen, and record. But it's okay. I will write in the chat. Okay.
Anyway, let's go through the basics of Google Colab first. Okay, can you see my screen?
Yes.
Yes.
Let me also open Slack. Okay, so welcome everybody. That's again the first session of the second day of the HPC Advanced Training event. So what you see now is a Google Colab document. It's been developed by Google, and it's been used extensively, I would say, by I think both industrial sector and academic sector in a lot of places to fastly prototype something and use a GPU that is provided by the Google runtime, or even a TPU, so a tensor processing unit. So as you can see, it's an executable document that lets you write, run, and share code with Google Drive. It's very similar to Jupyter Notebook. For those who use Jupyter Notebooks, it's based on that, let's say, but it's stored in Google Drive, and it's connected to the Google Cloud Runtime that allows you to execute Python code without any setup on your own machine. That's a functionality that we can have also on the supercomputer at Cyprus Institute. So we can have, let's say, a server serving some Jupyter notebooks, and the runtime will be on the supercomputer. So we can be able to use all the computational resources provided by it. So the notebook. The notebook's main components is cells that contain code, text, images, or other objects. It has code snippets to help you while coding. So if you're a beginner at someone, you can just go here, for example, and you can see how to install things, see how to visualize things, and so on. So you can get the code here, and you can insert it by using this button in your notebook and have some baseline to start implementing something. So it can be shared like a Google document, and we're going to use that functionality today. And what I'm using today is the text editor, which is Markdown. So you can see you can use Markdown, and you can add images or text or GIFs, as you can see, and it can render it in the notebook. What is important here is that you can find the runtime here. So we go here and we can use GPU to make training faster. And apart from that, you can export it as a normal Jupyter notebooks or as a Python code. Okay, that's for the Google Colab. So I'm here starting with importing the libraries we're going to use afterwards. Maybe they are not so important now. So matplotlib is used for plotting things, and we have Tensorflow, which is our framework for creating the neural networks, training them and using them, and Keras as well, NumPy here, and some other libraries that are not so important. So here we are going to use Tensorboard. Tensorboard is again something that is developed by Google, and it makes visualization of the performance of the network while training, for example, very, very easy. And so you can load this tool using this load external magic, as it's called in Jupyter notebooks, to load this module. Now going to TensorFlow Keras. TensorFlow has been developed a while ago by Google, and it's now probably it is one of the most popular frameworks to use in order to develop neural networks. It's free and open source, and it's a software library for fast numerical computing. It's developed and maintained by Google, and recently they released let's say the version 2.x of TensorFlow, which they did a good job in let's say consolidating the code and making it easier to work with. It's written in C++ behind the scenes, so I mean, even though we are using Python to interface with TensorFlow, at the end, TensorFlow behind the scenes is using C++ for the numerical computation, which means it's going to be fast. The good thing with TensorFlow, it's been designed to be used in research and development projects, but also in production systems. So big companies like Google, of course, they use it in their production systems. It can run on CPUs, on GPUs, and also on edge devices, for example, on mobile phones, and also on large-scale distributed systems like our supercomputer here. Now, Keras is a library built on top of TensorFlow, and in the beginning it was built to interface with this deep learning frameworks like TensorFlow or Theano before, or other frameworks. At the end, it's become a vital part of the TensorFlow library, because it's designed in a way to make building these neural networks very easy. It follows good practices for reducing cognitive load. It offers very, very simple APIs, and it minimizes so what the user needs to do in order to have a model. Good thing is that it also has a lot of example code that you can start with, and a lot of developer guides. And I said that TensorFlow is one of the most popular networks. It is one of the most popular ones, together with PyTorch, which is also open source and developed by Facebook. It's an excellent library as well, but at the end, what we want to do is to use to use one framework. It's a personal preference at the end if you want to use Keras or TensorFlow or PyTorch. But at the end, we are going to use it as a toolkit to help us just build training and train deep learning models. If you have any question up to now, please open your mic and ask. Okay. So the main object behind.
Sorry, I have a small question.
Yes, sure.
I would like to know just a sentence or two how PyTorch is compared against TensorFlow.
Yeah, for sure. PyTorch has been evolving, I would say, at a higher rate than TensorFlow the last years. So it's the kind of rule of thumb or the way it's used. It's that PyTorch is more flexible on some extent to be used for research purposes, and TensorFlow is the main tool to use if you want to start developing something and then you plan to put it in production, let's say, in a production system. However, PyTorch is being used extensively for production as well. So at the end, there are not many differences, I would say. It's one thing is that PyTorch is maybe more Python-like, the way you use it to use it, so the interface is more written in a more Pythonistic way, where Keras or TensorFlow it's a bit different.
Okay, thank you.
Thank you. So yeah, tensors are like let's say NumPy arrays, and it's the main object being used from TensorFlow to perform these numerical operations. Some differences that make it more attractive than NumPy is that it can directly leverage hardware accelerators such as GPUs and TPUs to make the calculations. It can automatically compute gradients of differentiable tensor expressions, and the computation can be distributed to a large number of devices on single machine or a large number of machines with multiple devices each. So in a way, TensorFlow has been built in such way to allow for let's say training very large models. If you're familiar with the NumPy API, the TensorFlow API is quite similar. So you can easily create vectors, including constant values. So you can see here, you can create a tensor just by providing a list of numbers, and it will output a tensor for you with the appropriate shape. In this case, we have 3 rows and 2 columns, and you can also have the value of the type of the values. You can get the value by calling NumPy on the tensor. So now you have a NumPy array, and you can inspect its shapes using the dtype or shape methods. So you can easily create tensors by filling them with zeros or ones using, again, TensorFlow methods. So you can specify, okay, I want to fill this with 1, and I want the shape to be 3 rows, 1 column, or the shape to be else, or even larger things. And you can also have normal values where you can draw the normal values, so you can sample from a normal or a uniform distribution like here. You can provide what the mean of the distribution you want to sample out from, and the standard deviation, and so on. So you can have also variables in tensors that hold states that can be mutated, so that can change. For example, the weights of the neural network is something that it changes as the network is being changed, it's being trained. For example, you can see here that you can start with an initial value of random initial tensor with random values, and you can create a variable from that initial tensor, and then you can assign new values to the same tensor. You can see here that the values change. So this is something that is being done while the neural networks are trained. So the tensors are used to hold the weights of the neurons in the network, and during the training they get updated. With TensorFlow, you can also easily do math, very similar to NumPy, as you can see now here. And yeah, that's mainly the very basic stuffs to get familiar with tensors if you are not familiar with. But the main point is that if you're familiar with NumPy and NumPy arrays, then TensorFlow is not that dissimilar to that. Any questions, anyone? Okay. All right. Now, going into more components of neural networks. So for the Keras library, it refers to the steps of the neural network as layers, which are the basic building blocks of neural networks. So a layer, you can imagine it as a computation function that takes in some tensor and outputs another tensor and some state for that, which is held in this TensorFlow variables, for example, the weights. Here you can see how you can implement a layer in Keras. So you can call the sequential API. So Keras has a lot of ways for you to build the neural networks. It has a lot of APIs. It has the sequential API, which is the simplest one. It has the functional API, and I think it has the models API, if I'm not mistaken. So I usually use the functional API because it allows you to have let's say multiple inputs, multiple outputs, whereas the sequential API, as the layer suggests, you cannot have this. You can have sequential input output without branching the network out. So again, going back, this is how you call that API, and then using the layers method from the Keras library, you can build here a dense neural network with just one neuron, very similar to perceptron. Another basic ingredient or basic component of neural networks is the optimizer. So optimizers are algorithms or methods that are used to change the attributes of the neural network, such as the weights and the biases, and also the learning rate. And the reason to do that is to, of course, reduce the objective function or the loss function. As the main objective of the optimizer is to minimize a loss function that is, again, can be defined by us, or Keras has a lot of predefined neural net loss functions that you can use. In Keras, you can choose the algorithm for the optimizer when you compile the model. For example, when you have a model, you run compile, and then you choose what optimizer you want to use. SGD is one of the main optimizers, which is the simple or vanilla stochastic gradient descent. So there are a lot of information about this in the Keras API, in the Keras documentation. You can visit this link to find more. Another basic component is the backpropagation algorithm, which is so backpropagation computes the gradient of the loss function with respect to all the weights in the network, and it has an algorithmic way to do that efficiently, so that this operation can be made fast. After this operation finishes, we can use the output to update the weights of this network. For those you have been in the field of neural networks, it was a big milestone when the backpropagation algorithm was introduced by Geoffrey Hinton I think 15 years ago. And because before that it was seen as very computationally inefficient to train these networks, and with this backpropagation, which is at the end a very clever way to perform the gradient, the chain rule, this allowed to train deep neural networks more efficiently. Next, we have stochastic gradient descent, which is the main algorithm that is used for training. So most of the optimizers use some version of the gradient descent algorithm, except, for example, the one that we have here uses the vanilla stochastic gradient descent to optimize the weights. There are many more algorithms. For example, the Adam optimizer uses gradient descent again, but with adaptive learning rate. And this algorithm has been the main algorithm to be used as an optimizer these days for training neural networks. Then we have the loss function. So the loss function is the function that is our objective. So at the end, we want to minimize the error in these networks. So what we do is that we go forward in the network, we compute the gradients, and then we start with, let's say, with some weights, and these weights have some error in our objective. For example, let's say we want to classify some digits as a computer vision problem. So we have some classifications. Using the loss function, we see how much our classifications differ from the truth, and then we use gradient descent and backpropagation to go back and update these weights in our network, come forward again, get new values, and have this approach to try to minimize the error or loss. And a way to introduce loss function in Keras is by providing a value for the loss parameter, for example, mean squared error, when we compile the model. Now going to activation functions. An activation function is a function that defines how the weighted sum of an input is transformed into an output. And activation functions are used to introduce most of the time non-linearities in the neural network. By introducing non-linearities, it means that the neural networks can become more efficient in approximating more efficient or more flexible in approximating a function. And in Keras, they are defined when building the layers. So when you build the layer here and before, so now we built a dense layer with 32 neurons, with activation function being the ReLU. And then an evaluation metric quantifies the performance of the model. So we train the model on a dataset, and we use the model to make predictions on a holdout dataset, which is also called the validation dataset or testing dataset. And it's really important to do that because the objective is to train the model on some data and then test the model on some data that the model has not seen yet. So that so when we go to a real world application, let's say we are not expected to have all data coming in. We expect to have new data coming in, but data coming from, let's say, assuming that they come from a similar distribution as the training data. And we can define the metrics again when we compile the model by providing some value for the metrics as you see here. Last validation is the process of evaluating on the model on the testing or validation dataset. And as mentioned before, is a holdout dataset that the model has not seen yet. And again, the idea is to test whether the model generalizes to new data. Okay, so that's all with the components. Are there any questions now? Please be free to just open the mic if you want to ask something. Okay. All right, I wanted to show you that you can use Jupyter notebooks to also embed YouTube videos using the display method from the Jupyter notebook. Here there is a video from a guy that does videos on maths and neural networks that provides a very nice visual way to explain them. We can see it afterwards if we have some time. And so again, summarizing, if we want to discuss about the main components of the neural network, we have, of course, the architecture, how we construct it, how many layers, what kind of layers we have in. We have the optimizer, we have the scheduler that we're not going to talk too much about the scheduler today. So the scheduler is something that can adapt the learning rate of the neural network. And then we have the learning objective of the neural network. So the objective is, what do we want to do at the end? Do we want to classify something? We have a binary classification problem, for example, classifying cats versus dogs. Is it a multi-class classification problem? For example, classifying the handwritten digits. Regression problems, object detection in the field of computer vision, image segmentation, and so in the field of natural language processing, for example, translation language model. So now the idea is to spend some minutes to try to build a network based on what we have discussed before. And the idea is to build let's say the hello world of the neural network. So the idea is to construct a neural network to approximate the function that predicts the prices of the house. So in this case, we know, let's say we know the function that we want to approximate with a neural network, so that provides us with an easy way to test it, whether the network performs well. And we can build up a function that's very easy. Like, for example, let's say that a house costs a basis of 50,000 euros, and each extra bedroom costs 50,000. So one bedroom house costs 100, two bedroom house costs 150, and so on. So for the exercise, you can use this notebook here. I'm sharing it in Slack. Please let me know if you can access it. And if you can access it, please copy a version of it on your Google Drive. If you have any questions, please let me know. Now, could you access it?
Yes, I'm okay. I could do it.
So that's the first exercise. So exercise 1. I have there the input. So the import that you would need to use. Do not forget to change the runtime to GPUs, although it's not going to be so important right now. We are not going to build a huge network. If you have any questions, also please use the Slack channel.
Sorry to interrupt. Can you please remind us how we set it to a GPU resource? Or
yeah, go to runtime.
Okay.
Go to runtime, and then from runtime go to change runtime type.
Thank you.
Let's spend maybe until 11, and then we can go through it together. And after, if you have any questions, please ask. One question, are you all in Slack? Because I'm sending some messages in there.
I am, yes.
So is there anyone that is not in Slack? Okay. So I take that you're all in Slack. Okay, maybe let's wait until 11:05 and then we can solve it together. Okay. Should we? Let's start going through the exercise. So that's a very simple example of how you can use nodes of a neural network to approximate functions. That's very close to what it's called a perceptron, which is just one unit in a network. And at the moment, I'm not sure that you can hear me. Can you hear me?
Yes.
We can hear you, but we cannot see your solution. If you were going, yeah. Okay.
Can you see the collab?
Yes.
Yeah. Okay. So let's start together. So let me bring the exercise here. Okay. So the idea is to provide the training data ourselves to the model. So, for example, we can provide the number of bedrooms, let's say, the type of, and then we can create a function, which is the function that we want our network to approximate, that gives us the prices of the house. So it's going to be in hundreds of thousands, something like that. And then we can convert also that to an NumPy array. So is it clear until now? So we just create the data that we're going to use for training the network. Okay, now we have to construct the network. We can use just a single, so a dense layer with just a single unit. So in this case, we don't really need to have an activation function, because what we want to solve is a linear regression problem. So our layer can just be like that. So it's going to be one single unit. So we have input, one node, and then output. After that, we have to compile the network or build the network. So for that, we choose two main things. So optimizer, we will go with stochastic gradient descent, and loss, we use mean squared error, which is one typical loss function to use for regression problems. So we're going to go with that one. And at the end, we want to feed the model. So to feed it, we give it the data, the predictions. So we have a number of bedrooms, and then we have the y's as the let's say the labels, so the results. So we give we have x, we have y. We can give the number of epochs. So let's start with something small. And for now, that's it. And hopefully it will work. So you can see here that what we do is that we fit the model. So we train the model for 10 epochs. And does anyone know what an epoch is?
The number of iterations that runs the model. So
it's the number of times that the model sees all the data. So each epoch means that the model has already seen all the 7 data points that we gave. So for the first epoch, it sees. So for the first one, the network has a random weight, let's say, and then it sees the 7 data points once. It updates the weight and the bias, and then it goes through it again, goes through all the data again, update again, and so on for 10 times. So we can let the model do that for more epochs, but you can see here that at some point it converges. So you can see that the loss, which is in our case, it's the same as our, so the loss is the same as our metric, so that our evaluation metric. And you can see that there is not a difference after, there is not a significant difference after the, let's say, it slowly goes down, but after the, let's say, 10th, 20th epoch, maybe it starts going asymptotically to conversions. Do you have any questions for this one here?
Shouldn't we use the tensors?
So we can convert that to tensor, but we can also in this case give it in here as an NumPy array as well. So the model actually can accept an NumPy array. So in the case that we have simple structures like a one-dimensional list, we can give it as an NumPy array as well. Can accept that. All right. Any more questions?
Can I ask something?
Sorry, come again?
I wanted to ask, I know this is an example. Can you hear me?
Yes, better.
But the training said we want it to be as big as possible.
Yes, so the idea is to have, I mean, if we have complex tasks, for example, image classification, the idea is to have, so the bigger the data set, the better the results we will have. But yeah, in this case, it's just a vanilla example to just see how, I mean, that we know, let's say we know the function, right? So we know that this is the function that we want to approximate. And we see that, okay, this is, we train the network so that at the end, the network has approximated that value. And we can also check that by calling a predict method. For example, let's say we have a new value coming in. I have to give it as an NumPy, as an array as well. And then we call predict. And you see that for 7 rooms, we get 400,000. So that's hundreds of thousands. So we get 400,000 euros, which we can see that it approximated the linear function fairly well. Okay, so if you want, we can do a 10 minutes break before we go in another task in computer vision. So let's say we can come back at 11:25, and I will stay online. So if you want to ask something, I will be around. Hello again. Are you all here? Okay, let's start. Okay, next. Next part is going to be on solving a computer vision problem. And briefly, computer vision is a field of study concerned with the problem of helping computers to see. It's always use it looks like an easy problem space, but because it's so effortless for humans. However, it's a very challenging problem for a machine. And before deep learning, it was actually much harder to solve this kind of problems. And with the advent of deep learning, it became let's say easier to progress the field. And taking from a book on model learning and inference, so at an abstract level, the goal of computer vision problems is to use the observed image data to infer something about the world, which is the way that is used for autonomous cars or robots and so on. And there are a lot of tasks that can be solved with computer vision. For example, optical character recognition, machine inspection, retail like automated checkouts. This has been already implemented by Amazon in some supermarkets in US. 3D model building, as well as photogrammetry. Medical imaging has seen a lot of advances in kind of using computer vision to assist doctors in recognizing features, let's say in an image, for example, X-ray imaging or CT imaging or MRI imaging and so on. Automotive safety, much move, motion capture, surveillance, and so many others. And so, anyone wants to ask something? Okay. So we can start the exploration of computer vision or deep learning for computer vision by having a look of what humans see and what machines see. So you can see an image here that is in a data set that's usually used for training deep learning models to be used for autonomous cars, right? So what a human would see, okay, this is a grayscale image, so it does not have the red, green, and blue channels, but we can use it as an example. But so the human brain has evolved to immediately recognize a lot of things like the road, the cars, street lights, shadows, the presence of the sky, for example, and so on. It can also infer from the brightness of the sky that it's day and it's not night, since it's a grayscale image. So at the end, the human brain, which is also the biological example that has been used to build these deep learning systems, has been built and evolved to do some heavy computational processing on the visual input that it gets. And apart from the heavy processing, it also leverages some built-in mechanisms to understand a scene, so to deliver an experience from what it sees. which is something very, very different from a machine. So it has none of the above. So no built-in mechanism. So any built-in mechanism has to be created by a researcher, for example. So that's what makes it a big research fee for AI researchers to artificially build in these mechanisms for the computer. So this is what humans see. Now, what do machines see? Of course, the computers only think in numbers. Whatever the data is, image, sound, music, in a machine, these are represented always as numbers or list of numbers or list of lists of numbers and so on. So we can see what the computer sees below by loading this image and printing it out as an NumPy array. Let's see where it works. Okay. So so here I have uploaded an image in my one GitHub repository. So the pillow library can be used to process that image at the moment. So what we are doing, we are getting the image behind this URL by using the requests model in Python, and then we open the image using the open method from the image method in or module in Pillow. So then we can convert that object to an NumPy array, and then we can see it here. So you can see the numbers which represent the light intensity. So I mean, if you look at it, it kind of makes sense because you have large numbers on the top, you have somehow high numbers on the bottom left, and then you have low numbers where there is shadow on the street, for example.
So this is essentially the grayscale, huh?
Yes, yes. So yeah, that's grayscaling. So in the case we have more channels, so we have red, green, and blue. We would have we would have 3 of these arrays, and this array represents each pixel. So each number here is 1 pixel in the image. So this is a 256 by 256 image. So 256 by 256. So we have arrays that are 256 numbers in the rows, and also 256. So we have 256 of these arrays stacked like this. So is this clear for everyone? Or do you have any questions? Okay, I'm going forward. One very important component in computer vision, or one very important development, are convolutional neural networks. So they are again layers of networks, the same way as the dense layers are, so that you can build neural networks by stacking a lot of convolutional layers on top of each other. And they have been very successful in computer vision. So they've been very successful for images. They have been also very successful for text as well, for natural language processing, though recent advancements in the field of natural language processing have evolved another kind of model to process and understand text, which is the transformers architectures, which are based on attention mechanisms, which is a way to it's a model to find out, for example, if you have an image, at which point of the image you should put more attention in order to infer something out of it. And these transformer models are also starting to gain ground also in the field of computer vision. But for now, we are going to use the convolutional neural networks that are now the main deep learning networks that are used for production systems everywhere. So the advantages of CNNs, as they're called, is that they preserve the spatial structure of the problem. So when we are dealing with images, it's important to somehow preserve the locality, the local structure, and then flatten the image to a long vector. So in the case of having a, let's say, multi-layer perceptrons or dense layers, what we would need to do is first flatten this image into a long vector, one-dimensional long vector of dimensions 256 by 256. So this would also result in having more weights or parameters when training the network, which means that we would need more computational power to train it. So the convolutional neural networks not only preserve the spatial structure, they also need less parameters to be trained. And what they do is that they learn the internal representations of images using small squares of input data, so small patches. So you can imagine the convolutional neural networks as small detectors. We also call them filters, that they are swept through an image, and they create representations out of that image. So features are learned through the whole image, allowing for the objects in the images to be shifted or translated in the scene, and still be detectable by the network. So if you want to detect, let's say, an ice cream in an image, it doesn't matter where that ice cream is in that image. You can detect it easily with convolutional neural networks. Whereas in the previous multi-layer perceptron model, you would need to have the object at approximately the same place to be able to detect it easily well. Okay, so I have here a link from research institute that you can draw numbers. So let's say we can draw the number 1, and you can see the guess of the network. So you can see the prediction of the network. So what you have here is the input layer. So this is the image that goes into the input layer, and then you have a lot of sets of convolutional layers and downsampling layers. So you sweep the filter through the images, you get some what are called feature maps. So you get activations on the image when you have a feature that is more pronounced. So for example, here you can see that this feature map can detect somehow this edge. This one here can detect this vertical edge, and so on. So at the end, you go into more abstract representations, and at the end you can classify the numbers. So if you want, you can also play with it here. Let me copy it in Slack. So no matter how you draw the image, okay, it is failing, but so the deeper the network, the easier it is to make it work. Okay. All right. If you want to play with it, you're free to do it. So now the next step would be to go through a data set together, and then maybe you can so the next exercise you can try to solve a similar data set by yourselves using first so the first approach of multi-layer perceptrons, and then using convolutional neural layers. conclusion layers. So one good thing with Keras is that it can provide us with a lot of data sets. So you can access them using the datasets module, and from there you can extract the dataset you need to work on. And you can use the load data function to not only extract the data from that dataset, but also separate them into training and validation or test datasets. So you can see here that we have a training dataset with 60,000 images of 28 by 28 pixels, and we have a testing or validation dataset with 10,000 images, again with the shape of 28 by 28 pixels. And here we can draw some samples from that image of that dataset and draw them. So for that we are using Matplotlib. So and we get 25 images out of the training dataset. So you can see here that we have clothes that are labeled like t-shirts or dress or sneakers and so on. And our task next would be to identify to classify, let's say, the image based on the 28 by 28 pixels. So at first, I would say we can go through the fashion dataset together, and then you can use the hands-written classification task. You can do it yourself. So let's start from the beginning, so we can load the dataset. And then we can load the data and separate them into a training and validation dataset. So now, since we have images with pixels of size ranging from 0 to 255, what we can do to make the training better is to normalize these values to be in a range between 0 and 1. So this will help the network compute the gradients more efficiently and avoid the problem of exploding weights. Again, you can see that as a recipe with a lot of steps. So load. If at any time you want to ask something, please do so. So we can go to models, and then we just select the API we want to use. So the first approach would be to do this using without using convolutional neural networks. So what we need to do is to take these images of shape 28 by 28 and flatten them into a long vector. So okay. We can do that by using the flatten function or flatten layer in Keras. Then we add on top of that a dense layer with 512 units. And now we need to specify an activation function. So we specify a ReLU function for that step. And so after that, we need to specify the output layer. So this is we have an input layer, and then we have a hidden layer, which is this one here. And then at the end, we will have an output layer, which is going to be the layer that is going to be trained to give us the results. So to give us the labels for the images. So for that, we have, again, a dense layer, and we need 10 units. We need, anyone do knows why we need 10 units? So here we can be flexible with the number of units here. We can put 1,000, we can put 20, but at the end, we need to constrain this to 10. Anyone knows what might be the reason?
The number of classes?
Exactly. So that's the classes we have above. So we have 10 types of clothing. So here we want to have 10 types of, so we need 10 classes. So we want to have the probability of these classes. And because we need a probability, it's a common practice to use as an activation for the output layer. If you want the probability of the class, we use the softmax function. Okay, so now we have the architecture. And now we can compile the model. Or let's say, I can use the word. So to that, again, we have our model defined here, and we call compile. And we need two main things to remember them. So we have the optimizer. We need loss. And we need metrics, so that we use for evaluation. So optimizer, we will use this version of gradient descent, which is called ADAM, which has this adaptive learning rate, which is a common practice to use that for a lot of tasks. And since we have a classification problem, we can use this loss. Categorical crossing. Okay. And then as a metric, we can use accuracy. We're done. Then we can feed the model.
You have a typo in accuracy, I think.
No. Thank you. So for that, we can keep the results of the model fit in a variable. Let's call it history. And we can fit the model. So to feed it, we need the training data, the labels of the training data, the number of epochs. And yeah, we can start training, I guess, with that. Okay. So now you can see that the expectation is to reduce the loss and increase the accuracy. And you can see that we do have this trend. It goes back. Okay, now you can see that it finished with an accuracy of 91%. 1%, which is not bad for 10 epochs. Or is it? Let's see. Okay, so you can see that it finished. Now, this way we have to wait until the 10 epochs finish, so we can of course stop it by interrupting the execution of the cell. But Keras provides a nice way to stop training as soon as we hit a certain value. So this can be done by using callbacks, and we can implement our callbacks. So callbacks are functions that are called each time, so at specific checkpoints. So what we are going to build now is a callback to check the accuracy each time an epoch finishes. So we can write a class, let's say a callback. Which is going to inherit from this class, and we define a function called onEpochEnd self, and then we give the epoch, because the accuracy is going to be read from the logs that are being outputted as the model is being fed. So if logs get, so logs is a dictionary, so we can access a value by the get function. So we can say that if the accuracy is above, I don't know, the value of 0.95, print something, print model then sorry, we access the stop training variable in the model, and so if this happens, we change this value to true. Okay, so this now is how we can build a callback, and we can now instantiate it by using okay. Now we have our function here, and we can call it in fit. So we can have a variable called callbacks, and give it a list the callbacks we want to provide. Okay. So let's try this. But this is a very nice way to, I mean, to not spend computational resources trying to reach a value that you don't want to reach. So if you are satisfied with having an accuracy of 95, for example, you can use this callback to make it happen. Now it's not going. Anyone knows if this is going to work? The one epoch to end. So this is not, so with 10 epochs we are not going to reach 95%. So this cannot, so this will not turn to true. And but just to make it, just to show it to you, so let's do this 0.9. Okay, now it's 90, so let's try again. So you see at epoch 6, we reached 90%, so the training was cancelled. Any questions?
So basically the accuracy is going to be 9 out of 10 for the labels.
So yeah, it's going to be 90%. However, this is the accuracy on the training dataset. So one good practice is to train on the training dataset and also get the accuracy on the validation dataset. And to do that, we can use, so we have the data already, we have data, so here is the data. So we can provide this data to the model as well. So for example, we go here and we provide the validation data. So now, there is sometimes that Google Colab can freeze, at least for me it happens frequently. Let's see. Okay, so if this happens, you have to load the libraries again. And then go back where you were. So you can see here that you see first, the loss and accuracy on the training, and then as soon as that finishes, it checks what happens with the validation data as well. Okay. Okay, I think if you have any questions, please go on. Otherwise, we can go to the second exercise of implementing this on a different data set. So you can see it on. So that's the other data set is called MIST. Dataset. So this is the one that I used here is called Fashion MIST, which is created by Zalando, German retail store, and the MIST one is so you can also view it in the notebook, but so there are the 110 data digits that we also saw here. Okay, so if you want, you can proceed to the second exercise, and we can wait 20 minutes. Yeah, and if you have any questions, please either ask here or please ask in Slack. Can you hear me?
Yes.
Let's maybe start with an has anyone managed to finish the exercise?
Yes, exercise 2, you mean? Or,
Yes.
yeah.
The rest, if you have any other trouble, you can yeah, please send something on Slack or say so that we can support you. Okay. So after next step, after solving the image recognition problem using the dense layers, would be to use convolutional layers with pooling layers together. So we can go again through this step by step. Give me a minute. Give me a minute. Okay. So we can reuse some things from before. Let's see. So up to here we were doing the same things. And now let's use Tensorboard in order to be able to visualize the accuracies and the losses in this case. So Tensorboard can be used for visualizing a lot of things. So you can construct your own metrics and add them. But for now, we are going to use what is provided, right? Okay, so we have Tensorboard, and then let's define the architecture. Okay, so our model is going to be again use the sequential API, and we have this means that we have a two-dimensional convolutional layer, which is typically used for images. We're using 64 detectors or filters with kernel size 3 × 3. So that's the detector size. So if the image is 28 by 28 pixels, this is going to be 3 × 3 pixels, and it's going to sweep, so to apply convolution using this filter across all the image. Does anyone know? So in the cases of the dense layers, what we are learning, what the model is learning, is the weights on the edges of this layer. So can you see the brush on my screen? So you have. Let's see. Can you see it? Anyone?
No, just the cursor.
Yeah, we see the cursor.
Okay.
You can use the annotation tools.
Yeah, let me use that. So what we have, let's say, is that we have one layer here, one layer here, and one layer here, and what we are learning at the end are these weights and some biases. Do you know, anyone has an idea what we are learning when we are using convolutional layers? Any guesses? So
I guess we have a two-dimensional filter like we do in vision, in image processing, and we're learning the tops of that two-dimensional filter, so it's a kernel again.
yeah. At the end, if you imagine that filter as a square like this, okay. what we are learning are these weights. So we have a lot of detectors or filters or kernels like this, and we are trying to learn these weights so that we allow the network to detect different kind of features using these weights here. Right, where am I? Okay, here. Okay, we were defining the model, so we have 3 times 3. So the 3 by 3 kernel is so it is one of the most popular choices of the sizes of the filters. So if you use bigger filters, you have more weights, and the training gets longer. So at the end, that is in most of the cases that the filter used is 3 by 3. And we're going to use the same activation function like before. And we keep the input shape. Okay. So that's the first layer. Then apply a pooling layer, which again, sorry. So this at the end it compresses the image. So at the end we from an image file size of 28 by 28, after the convolution we will have 26 by 26 of filters, and then the max pooling will decrease the size even more. So at the end, the usual way you construct the convolution layers is to always have a set of convolution and then a max pooling. So the max pooling will apply a patch as well. So like this, 2 by 2 pixels. And since it's a max pooling, it will detect the largest value from here, and then output it to a new tensor. So we have now the convolutional layer with the max pooling. Then we need to construct the classifier. So we need to flatten that tensor. And we start passing it through and again, since we have 10 labels, so we will use the last layer, so the output layer as our classifier. So that will output probabilities as well. So now, before we build the model using okay, and then we feed it. Here we are inserting the callback that we created above. And also we can also insert the TensorFlow callback, which we created here. That is going to use the logs and extract them to Tensorboard, and Tensorboard can plot the plots. This is called. Okay. And then, sorry.
Are there any more parameters in the convolutional 2D parameter?
For this, sorry, come again.
If you scroll to the right after input shape.
Right. Here.
That's right, thanks.
We don't need to add anything else at this point. So we need the activation function, the number of filters, the size of the filter, and the input shape. And what we also need to do is to so since we have the first layer is now convolutional layer, we need to reshape our data to be able to insert them in there. So here we need to reshape them. So what we do is we call reshape, and we have 60,000 images, 28 by 20 pixels, and one channel because it's grayscale, and we have already normalized them, and we have and we have 10,000 of them. 28. So you can find the so the load data already does this type of split. We can specify the splits in here, but since it by default it comes like this, let's use it like this. Okay, I think we have everything. So you always have in mind that when you use callbacks, they might slow down things. Screenshot for split one. One sees where the problem might be. Okay.
You are missing the Tensorboard log dir logs percentage.
Yeah, but I think we have a problem before that, right? Sequential for expect money basic twin tensors. I think we have a model with a program with tested. Test. Machine.
Mine works.
Yeah.
Mine too.
Let me copy my previous. Okay. Okay.
What was your model accuracy? It was set for the call path.
It was set 90. Let's set it to 99.
And yours converged to in which epoch?
Well, it didn't converge. It just stopped after the second one. So
okay.
So it went, the training accuracy went to 90% after the conversion. Oh. Okay. In the meantime, you can, for those you that have not done it, maybe you can proceed to the third exercise in the Jupyter notebook.
Can you show us once again the reshaping so that it works with a 2D?
Yeah.
Yeah, thanks.
How are you going, everyone? So it's 1 o'clock, so it's time for a lunch break. And actually, I think we are finished. So if you have any issues with the exercise, again, please ask in the channel. So you can ask in the channel we have dedicated for this training, or you can send me a personal message in Slack. And yeah, that would be all for today. Before we go, so let me stop sharing. Before we go, I was wondering whether you would like to have a more kind of extended training on neural networks, so we can have a project of that might last, I don't know, one month, and we can use Slack to communicate with each other, so that and we can have a problem, and so you can the task will be on you to solve it. But if you want any help, you can always contact us on Slack. So if you want something like this, please say so on the chat here in Zoom or in Slack channel, so that we could prepare for it as one next kind of EuroCC activity. I mean, in this case, we can use bigger data sets, and also we can construct deeper models. So that we can have this training on a more kind of constant basis, let's say. I see Christos and Timos, they are interested. Anyone else, if they're interested, again, please say so. Of course, we will have an evaluation Google Sheet also at the end of the day. So please, for a review on the training, please use that. But I hope you found it interesting, and so I hope you have now some basic knowledge for those that didn't have, to construct some neural networks. Yeah, so thank you very much, and let's go for a lunch break. And the next trainer will be Nikos at 2 o'clock.
Thank you. It was very good. Thanks.
Thank you.